Let us see few more properties of Z transform, which are important properties for tackling the numericals on Z transform. First property is the differentiation property. What does this property state? That when we are taking the derivative of the Z transform, okay, so we are having the x of z as the Z transform, d by dz of x of z, that is the derivative of x of z. So what happens to the time domain signal? Okay, so when we are taking the differentiation of the Z transform in the Z domain, okay, we are actually multiply it leads to multiplication of the signal x of n with n in the time domain. So you have to remember this property like this. Okay, so simply the differentiation of x of z in the Z domain leads to multiplication of x of n with n in the time domain. Now to prove this property, we have to use some mathematics. We have to rearrange the terms. Okay, so I use here the definition of x of n, x of z. So this is my x of z. I can use the definition of Z transform x of z here. Now look carefully what we want on the RHS. Okay, so LHS we have n into x of n. So what will be the Z transform of n into x of n? It will be simply n into x of n z raised to minus 1. So instead of x of n we have n into x of n. So we write here. Okay, now we will try to put here in this equation in the RHS z into z raised to minus 1. This is simple substitution. And why we put this? See, z into z raised to minus 1 is equal to 1, because this is not going to affect anything in if we put this 2z, 1z and 1z raised to minus 1 into this equation. But it will serve our purpose of proving the RHS. Okay, so we just put the substitution z into z raised to minus 1 is equal to 1. Okay, this is actually equal to 1. Okay, so when we put over here, then we can see here that if we put here after this, okay, if we take minus z outside, so if we are taking minus z outside, here we have to add a minus sign here, so that minus into minus will become plus. And here in this equation we can have z raised to minus n minus 1. Okay, because 1z we have taken here outside. Okay, now if you see here, this is nothing but it is the derivative of z raised to minus n. So what is the derivative of z raised to minus n with respect to z? It is minus n z raised to minus n minus 1. Okay, so minus n z raised to minus n minus 1. Okay, so here if you see, okay, so minus z is outside. I have taken minus z outside. Now simply d by dz also I can take outside the summation, and inside the summation I will have only this part, which is nothing but my x of z. Okay, so this is nothing but your x of z. Okay, so I can write here simply this is x of z. Okay, so Z transform of n into x of minus n, sorry, n into x of n is nothing but minus z d by dz of x of z. So this is what is the property of differentiation property of Z transform, which is called as the differentiation property of Z transform. So how to use this property solve a numerical? Okay, so suppose we are asked to find out the Z transform of n into x of n. Okay, and x of n is given like this. So already we know the Z transform of x of n, which is z upon z minus 1, and we are asked to find out the Z transform of n into x of n. So if you look carefully, n into x of n, which is nothing but matching with this. Okay, it is matching with our LHS. So what will be the Z transform of this n into x of n? It will be simply minus z d by dz of xz. So it simply see this is my d by dz. See, sorry, this is my x of z. So this is my x of z. Okay, so if I take the derivative of this x of z, okay, if I take the derivative of this x of z, derivative of z upon z minus 1, and just multiply it by minus z, if I multiply this by minus z, I will get the Z transform of n into x of n. So that is so simple. Okay, so by using the differentiation property, the Z transform of n into x of n will be simply minus z into d by dz of xz. So in place of x of z, I substitute here this z upon z minus 1. This is given because it is given that the Z transform of x of n is z upon z minus 1. So I just put here z upon z minus 1. Now I take the derivative of this z upon z minus 1. So u by v rule we can apply. So it is simply z minus 1, derivative of z is 1 minus z into derivative of z minus 1 is again 1. upon z minus 1 bracket square. So this is u by v rule of derivative. Okay, differentiate how to take the derivative of two functions u and v. So this is the formula. Okay, so now after rearranging the terms and opening the terms and solving it algebraically, final answer you will get upon z minus 1 square. Okay, so simply by you making use of the differentiation property here, we are able to find out in just 2-3 steps the z transform of this function, which is n into x of n. So it is so important to remember the properties of z transform, and we are seeing here how the properties of z transform are making our task easier to solve the numericals, because this z transform n into x of n is very difficult to solve by the formula, because here already x of n is having the z transform. So first you should know the z transform of x of n, then x of n multiplied by n, so summation will be very difficult. But if you make use of the property of z transform, then it becomes very easy here. Okay, so these fundamental equations we have to remember and try to see what is given, what is the signal z transform is asked, in which property does it fit, then use that property in order to solve the numerical. Like next we will see the convolution property. The convolution property states that now when we take the convolution of two signals in the time domain, the z transform, what happens to the z transform, it is simple multiplication of their z transforms. See this symbol asterisk, which is reserved for convolution. Okay, this asterisk is reserved for convolution, and this is dot sign refers to multiplication. So the property is that convolution of two signals in the time domain is multiplication of their z transforms. So when we are having two signals given in the time domain and we are asked to find out the z transform of the convolution of those two sequences, simply what we can do is we can find out their z transforms and just multiply them in the z domain in order to get the z transform of the convolution of the two sequences. So this is so simple. Okay, so how to prove this property? For proving this property, we should know the equation of convolution. So this equation of convolution we have already studied in the first section. So this is my x of n, h of n, then x of n, x of k into h of n minus k. So instead of h of n, we are having here x2 of n. Okay, and instead of x of n, we are having here x1 of n. So this is my simple equation of convolution. Okay, by definition we can write the z transform of x1 of n as x1 of z, then the z transform of x2 of n as x2 of z. Now if you substitute this convolution equation into this formula of x of z, okay, so I can have the double summation here, because already one summation is for n and another summation will be for k. Now just to put here for substitution z raised to k into z raised to minus k, which is actually equal to 1. If you multiply these two functions z raised to k and z raised to minus k, the product will be equal to 1. Okay, so now I put these two extra terms into this equation in order to separate out the summations. Okay, in order to get the two z transform we do this. Okay, so just we put up here. Okay, and this actually it is there. See, this summation is also there, it has been not written over here. This summation is also there. So here we get the two summations. So one summation is for n, another summation is for k, and you separate out the terms now. Separate out the terms. Okay, so you put extra terms here. So take this z raised to minus k here for this x1 of k, z raised to minus k for this x1 of k, and take this two terms z raised to minus n and z raised to k here. Okay, and take this term here x2 of n in this side. Okay, so what you will get, you will get here one summation equation, this is one summation equation, and this is your second summation equation. Okay, now this is very simple, we have got this transform here, but what about this? Okay, so again we have to do the substitution. Let n minus k is equal to p. Find out the limits. So when n tends to infinity, p will tend to infinity. When n tend to minus infinity, p will tend to minus infinity. So put here the limits now. So I will change these limits now. So n tending to minus infinity. So p tending to minus infinity to infinity, x2 of p. So n minus k is equal to p. So I'll get here z raised to minus p. So n minus k is p. Okay, so I put here p. So this is nothing but my x2 of z. So this is your x1 of z. This is your x2 of z. So in this way, we can see that where the convolution of the two sequences in the time domain is simply the multiplication of their z transforms. So this is the proof of the convolution property. We will see numerical in the next lecture.